So we've been building up to this point, and now it's time to cross over and actually talk about what the class is about, which is about, at least from the technical side, we've been building up to this point of understanding weapons. So what we've been doing up to this point is try to give you the fundamentals so that you can understand what goes on. You have to understand about a cross-section in order to understand a reaction rate. You have to understand about reaction rates if you want to understand about criticality and about thermonuclear reactions. And you need to understand this whole idea that neutron-induced reaction cross-sections get big as the neutron slows down. For thermonuclear reactions, when we have charged particles, you have to move fast enough that you can actually get in over a Coulomb barrier and have the reaction take place at all. All of that's needed so that we can start talking about weapons. But before I do this, I was engaged and excited by Professor Knott's discussion about the French nuclear weapons program at the end of our last lecture. So I've had a number of interactions with some really bright scientists from Marillion, which is their Defense Application Militaire branch of CEA. So they have like CEE, the Energy Commissariat, we have DOE, and they have DAM, which is like our NSA. Okay? And they're brilliant people, they're really good scientists, and frankly, they have some technical capabilities that we do not have. What? Good question. Well, probably a lot, but I'll tell you the little piece that I learned about, okay? We have this picture in nuclear physics that neutron-induced reactions are generally the same, whether the reaction cross-section, whether I measure it in a lab using a neutron beam and a nice controlled experiment, or whether it's taking place in a bomb, or in a star, in any sort of a plasma environment. Plasmas are just really hot states of matter where the electrons are stripped off the nuclei. We generally believe that this is not the case for charged particle-induced reactions, because there's charge, the fact that you're in a plasma and the plasma is charged affects things. But the neutron-induced reaction is supposed to be independent. Now, we've just begun to play around with this concept that maybe that's not the case. Just really started. And a lot of this came about because of a place called the National Ignition Facility. Raise your hand if you've heard of NIF. Okay? And now, please be honest and raise your hand if you've never heard of it before. Okay, good. So NIF, you give me an excuse to talk about it. I worked there for 6 years, so I guess I can talk about it. NIF is a big laser that concentrates all its energy. I'm going to talk about this later. Concentrates all of its energy on the inside of this little tiny centimeter long, half-centimeter diameter can, and heats it up and creates an X-ray bath. And then there's a little capsule inside of that that contains thermonuclear fuel, deuterium and tritium, and it basically implodes that capsule. And you're going to see that in today's lecture, like my discussions about that in weapons. So we've just started to look, because NIF is now getting a significant nuclear yield. It's not achieved ignition, it probably won't ever do it. But it is achieving a significant nuclear yield. We're able to start looking at neutron-induced nuclear reaction rates in a plasma. And we can explore whether there are any differences. Well, this involves trying to couple two different fields of science, plasma physics and nuclear physics. And really, when it comes to neutron nuclear physics, they're really different. The mindset is different. And none of the foundational work is the same. And so we started to do that, and it's tough. A lot of the atomic physics that's involved in plasma is irrelevant to a neutron. Neutrons don't care about that atom. They don't see the electrons. It's irrelevant to them. And so it turns out, though, that when you begin to look at the first thing I did as a researcher was I look in the open literature, and I see all these folks from Areal who've developed codes that do this, reaction model codes. There's one called ISOMEX. They use isomer excitation, okay, and I would call it ISOMEX, but it's their code and they call it ISOMEX. That's reasonable. And they were very sophisticated about this. So if I have an interaction with the scientist, when I was in Livermore, I had an interaction with a scientist from Marillion. It has to be somewhat scripted and organized. We do everything with the Brits, completely. They have Q clearances. We have UK secret atomic clearances. We tested with them. They are about as inseparable, I think, from a technical perspective as any country could be from the US. But the French are not like this. They're different. They're separate from us, and they have this separate ability. So we have this formalized interaction. I'm going to discuss one of those right now. So about 4 years ago, we had a collaboration with this group at CEA-DAM on how nuclear plasma interactions could populate the first excited state in uranium-235. Now, U-235 is a really strange nucleus. It's really important. It's at the core of basically all conventional nuclear reactors. Okay, it is the naturally occurring fissile isotope that we have. Okay, with its 7.04 times 78 year half-life. So it turns out, normally when I write a level scheme, the number here on the right-hand side is the energy in kilovolts. But here, this is not drawn to scale. This is U-235. The ground state has an angular momentum of 7 halves and what's called negative parity. Don't worry about that in a moment. The first excited state has 1 half and positive parity. That, for those of you who are technical, you know that is a huge difference. Okay? That state, though, the really amazing thing is that it's only at 76 electron volts, not kilo electron volts, just electron volts. That's really low. And as a result of that, in part, and the fact that there's such a big difference in angular momentum, this state lives a very long time. It's about 26 minutes. Okay. Now, the part of it, so that state, there was this interesting idea that was proposed. The first time I heard it was from a guy named Jerry Hale, who's a reactions modeling person in Los Alamos. He suggested that that state would have the same properties as the ground state of plutonium-239. Now, if you look at the cross-section for fission on plutonium-239 versus uranium-235, what you see is that in general, plutonium-239 is a lot bigger. Plutonium-239 is very fissile. In fact, early nuclear weapons had a problem with this because you just tickle plutonium a little bit and it fissions. And often you want to keep things kind of quiet before you actually hit it and start doing fission healing. So there was this prediction that in certain plasma environments, like maybe the interior of a weapon, you could populate this first excited state because the energy was so low that you could just boost it up. And this could have really important impacts, obviously, to nuclear weapons physics. If a piece of your weapon was made of uranium-235, and all of a sudden it started to behave like plutonium-239, it's not a plus, it could be a minus, unless you designed for that and planned for bigger fission cross-section. Okay? So we contacted the French, and we had a little bit of an initial discussion with them about what we were going to do. And in general, we do not perform experiments with fissile isotopes in NIP or any other laser facility. It's what's written into our environmental impact statement, okay? Which one could joke is far more important than classification. You never want to cross the lawyers, okay? So we don't do this, but we could pick a surrogate type of material. And it turns out we did. We picked one. Oh, yes. By the way, the NNSA's assessment of this, when we did this formalized thing with the French, the NNSA side of things, Washington wrote that this is, I'm paraphrasing dramatically a very complimentarily written letter. It was basically neat physics, fairly far-fetched idea. That was their idea. This is kind of perfect. This is like, like chocolate chip cookies and Doritos to a physicist. Sounds exciting. So we all got really excited about doing this, especially the fairly far-fetched idea. We jumped for that. So we came up with a neat alternative, which was to look at this nucleus Thulium-169, which also has a low-lying excited state that we thought we could populate through an interaction of plasma. And we shoot these laser beams into this thing that looks like a sideways top hat. We call it a half ROM. Okay. And the interior was coated in thulium, and the thulium would blast out, and we would take pictures of it. And by the way, we really do take pictures. I'll get into them when I talk about testing. In the end, if you want to get a really quick image, nothing beats film. You don't have something better than that, okay? And so we're going to take pictures and see if we excited that state. That was the whole idea. Now we spoke, the whole idea would be that we would run the experiment at the Laboratory for Laser Energetics at the University of Rochester, the Omega Laser, and the French would use their cohesiveness to interpret the data to see if the plasma excited the state. And like I said, the experiment was deemed completely in the basic science arena by DOE. But the French side demurred. And this is the first time that this had happened in our experience. Basically, they said, we can't participate. I had a couple of really awkward meetings with these scientists who were just friends. Like, I mean, I ate cheese board pizza with them and stuff, and they came over. All of a sudden, they said, I'm sorry, we can't talk to you anymore. And when I went back to the people at Livermore, and I said, help me, I can't play with my French colleagues any longer, they said, tell us more. Okay. So it's still, I don't know where this story went. At some point in time, the French came back, and they said, good news. We've been allowed to play with you, but we have to modify the proposal, and a couple of people are going to be pulled off. And I said, okay, that's fine. Do what you need to do. I'm looking forward to working with you. And just send me the review, the new proposal. And he said, no, we can't do that. So I said, so I'm going to collaborate with you on an activity that I don't know about with people that I don't necessarily know. And they said, yeah, that's basically it. Okay. The truth is, this was too stilted, actually, for things to continue. We decided to let this project rest. But I still, to this day, sort of think that the French know a lot more about laser plasma interactions and the excitation of states by plasmas than we do. Yes?
So what do you think caused this rift? Was it like you think that they just didn't want to share all this information, or?
Yes, I think this is completely speculative, but this is fun. I realized after that's one of the neat things about being in this classroom, right? We can have this. I think they know how to do things like this. I think that they can basically, the power that would be involved in this, you could alter a nucleus to have one set of cross sections at one point in time, and then put it in an environment where it has another one. And in nuclear weapons, the big thing you're going to get when, hopefully at the end of this, is that timing is everything. It's not a question of just blowing things up and it all sort of works out. There's really an intricate dance, and things have to happen at very specific times. If I can suddenly jump from one curve to another, that could be a big advantage. It could put me into a situation where, to be frank, I need less material to be able to make the weapon work. Or perhaps I can change certain aspects of the output of the weapon to better suit my military purposes. So the one thing also to always remember about nuclear weapons is they're not just these doomsday devices that destroy the world. Generals design their plans around this device performing in a very specific way. And they want it to be robust in that way. Anything that gives you design freedom is a plus. So if they have some way of doing that through this magic of nuclear plasma interaction, that's great. Okay. I will say that there are very sophisticated operations. And also, by the way, like Briere-le-Châtel, or B3, as we call it, that's a real weapons lab. Okay, like Livermore, there's a lot of science that goes on at Livermore in this house, really a lot, with really good scientists. And it's actually that most of the labs are very open, and a lot of the activities are open. Most of the employees that are there don't have clearances. You have 3 others, not like that. Okay, you go to bathrooms, there's guards working. Okay, it's a weapons lab, and they are very sophisticated in what they've developed. And I now understand that they had the same effective reason. It wasn't quite phrased so beautifully the way that you would refer to it, but they always lose wars, and so the whole point is to not get into war. Okay? And
so I have a technical question on this. I mean, sure, maybe in a secondary where you have a plasma environment where this kind of data would impact that. Say the primary only, what fraction of the yield is actually being generated in the plasma environment? Or by the time you reach a plasma, have you already fissioned most of you?
So the detailed answer to that question isn't something I'm going to get into. And the detailed answer also varies on the individual environment. It would be a design parameter. Part of the rules of nuclear weapons is, you've been given these cross sections by nature. use them. If I could suddenly jump from one curve to another, yeah, that's a new capability. That would give something that I didn't have before. And so I could design that, okay? So, all right, time to get to business. This is our picture, right? Yes?
Sorry, one
No.
more question.
Oh, I like
Can
this.
you
Good.
explain what plasma is and like where it
Yes.
occurs?
Plasma occurs up there. You know, all these lights over here. When you look up at the sun, you're looking at a plasma. Your elementary school teachers lie to you. They say there's 3 states of matter. There really isn't. There's at least 4. Plasma is one of them. When you heat matter up at the big deal, you know how we've got electrons orbiting the atom? The electrons can get knocked off. It really actually doesn't take very much to knock them off. Okay? And then they move independently. So that's a really different form of matter because it's got charge. Each individual nugget of it has charge. An atom, which is an equal number of protons and electrons, has no charge. So a plasma is a state of matter where the electrons, at least some of the electrons, have been stripped free of the atom. And now the two things move as sort of two coexisting interdependent liquids relative to one another. Okay.
What are like those 2 things?
The electrons and the remaining atom. Okay. So fluorescent light bulbs work by this principle. So does the surface of the sun. And that's why it glows. Okay. Plasma's got other weird properties, like you can use magnets to bend it. You can't use neutral matter to have magnets bend it. Like if you go up to me, well, around with a magnet, nothing's gonna happen except on credit cards, sure. But you know, it's gonna all be fine. But if you go up to a plasma, then it'll warp itself around because the magnetic field interacts with the charge, the free charge that you've got. Is that a good description for her? She works with plasmas, so she always does. Okay. So here's our picture. Let's go into details. So I'm going to recover a little bit that I showed in some slides before. It's been a little while since we discussed this. Okay. So the first weapons produce virtually all of their energy from fission, and that's what we call a primary. Okay. So to make a runaway fission reaction, what we need to do, which is what a weapon is, the primary is, we need to optimize the terms of the nuclear reaction rate equation. This is that reaction rate equation. It says if I have a target which has a certain density and a certain thickness, and I throw a certain number of particles per second at it, and each one of the nuclei in that target is a certain size, a certain cross-sectional area. The product of these 3 things will give me the reaction rate. Okay? Now, we can't do anything about this except choose the right nuclide. So now we get to the point that was just brought up here. Okay? Maybe we can. Maybe the folks know how to change that term. We don't. Okay? I don't know how to do that. It may happen a little bit in stars, and we've used that in some theories, but like the things in the sky. Okay? This is just a meaningless quantity for rate. It's how many times I throw something at it. Okay? Obviously, if I throw things more frequently, you get a higher rate. Okay? It's this part. This is what primaries try to exploit. It's the areal density of the target. We can assemble a dense large mass of one of these fissile nuclei, like U-235 or Pu-239 or U-233 for that matter. Okay? And if we change it and make it denser or larger, then we can increase the reaction rate. So obviously you can just stack more and more material, and I'll flash up a table show you that. What you find is that you need rather a lot of material to get rho r big enough to get to a runaway critical reaction rate. Okay? Or you could do this game, right? You start with a sphere of metal, exactly, and you compress it. And I gave this little notional thought. I'm not saying 4 is a magic number, but you can do this nicely in Excel using the animation, PowerPoint using the animation. You can shrink by a factor of 4. Okay, and now if I do that, if the mass is constant, what happens to the density? Well, the density goes way up. So remember, density is mass per unit volume. And the volume goes like 4/3 pi r cubed. So what happens is by shrinking this by a factor of 4, I increased the density by a factor of 64, because 4 times 4 is 16, times 4 is 64. Now, to be fair, you don't get to claim all credit for that, because now the R is smaller. And remember that it's not the density that matters, it's the density times the thickness, okay? And so if I multiply that 64 by the new R, which is 1/4, I end up with 16. But still, you see the impact of this, right? I haven't brought in any more fissile material, and yet I've increased the reaction rate by a factor of 16, just by pushing that metal and making it into a denser assembly. So who here has ever compressed a piece of metal by a factor of 4? That's not easy, okay? And by the way, who has even compressed metal at all? Who here has ever had a Coke can and tried to crush it in their hands? Yeah, if you haven't, then that's kind of interesting. Okay, can't do it so much with plastic. What happens with the Coke can as you start to crush it?
Eventually, like one part will rip and it ends up cutting your hand. And
That's true. So a lot of people say, stop work, stop work. No, that's right. Well, what happens is something juts out and breaks, right?
Yeah.
Okay? It's not uniform. Try to compress metal in a uniform manner, okay, without it squirting out and cutting your finger, okay, is really hard. It's really hard. Metal doesn't tend to do that, okay? And so you really need to know a lot about the properties of matter to be able to do this well. And just to make matters worse, the matter you need to know about is like plutonium, which is awful, okay? This is not a friendly metal at all. It's toxic, okay? It's hard just to make a large amount of it, meant that you need to have reactors running for a very long time. It kills you if you hang out around it. It bursts into flame and air. Okay, it's bad. Okay, so really, let me just rest assured. If I gave a sphere of plutonium to a terrorist to say, go ahead and figure this thing out, yeah, that's not going to happen, by the way. Actually, plutonium is probably going to kill them almost immediately. Yes.
Like, where would you find a sphere of plutonium?
eBay, no. No, really. Where would you find one? They're really, this is the provenance of weapon states, and they keep them very secure for the most part.
But like, where do weapon states get like plutonium or uranium?
I will go into that. Plutonium, I mentioned it in some slides earlier. Plutonium can be made, it's mostly plutonium-239. That's the one I'm talking about here. By putting uranium-238 in a reactor core, most fuel is that, and the uranium-238 captures a neutron, it becomes uranium-239, and then it undergoes 2 beta decays, and it becomes plutonium-239. And now, because it's a different element, I can chemically separate it. I can only separate things with chemistry if the atomic number is different. And so I can then separate out the plutonium and use it. But you need to run a reactor for a very long time. Okay? Even the biggest reactors that we have, generally speaking, over the course of a year, produce a very modest quantity of plutonium. Okay? And then you need to reprocess it and get it out. Okay? That's sophisticated. It takes a lot of work. Yes.
Was this stuff ever sold on like Silk Road or a darknet site?
Was it ever sold where? Sorry,
Silk Road or
Silk Road? Oh gosh, I don't know. I only know that from like Law and Order. No, my suspicion is probably not large quantity. I mean, really, the truth is you need to be a pretty sophisticated actor to be able to get it. Plutonium in particular. Now, U-235, that's a different story. It occurs in nature, but we will discuss that also. I do have a half lecture planned for later where I'll talk about how you enrich that, the U-235 content in uranium. Okay, but you do need to have that to get this started. Yes.
Let's say we have this sphere of plutonium.
Yep.
How would it be like transported from like do you put it in a big metal box, or like what is the how
do you transport it down to smaller size, or how do you
how would it be transported? Let's say we have like a sphere of plutonium.
Right. I've seen
one
plutonium
lab,
spheres. They are generally coated in nickel. That helps keep them a little bit safer to move around.
or like for example, one lab is transporting these to another the spheres.
If they were doing that, how is the transport done? That's an interesting story in its own right. That was in my nuclear weapons orientation course. It is actually, in some cases, we do move material around. When we do that, it's done surreptitiously. And the people who are doing it look to you like ordinary truck drivers, except they're not. Okay? And the guy who gave the course, he was a colonel, and I'll remember his name if I don't think about it too long. He said they love killing people. So give them an excuse to kill you. They actually are going around guarding this material the whole time it moves. And when they move it, they tend to move it in quantities that are so small that even if it were intercepted, it wouldn't be movable. But it is very well monitored and kept track of. We have national and international databases that keep track of this down to the sub-gram level, plutonium in particular, okay, but uranium-235 enriched material as well. So it's carefully transported.
Why?
Why?
Like
Because
it's so hard. It's like so hard to create a weapon and
redundancy. Your goal in non-proliferation is to set up multiple blocks so that you can't get the material. Okay, you got the material. You can't get the processing. Okay, you got the processing. We keep setting up roadblocks at every level to try to slow things down, basically. And nations can get over this. They have the capacity to do this. And no doubt that Iran could develop nuclear weapons. Okay, I mean, all nations can do this. They have it, but not individual actors. It stretches the realm of believable to think that a couple of people hanging out in their garage. That's not going to happen. Okay. Okay. All right. So let me go forward. Right. R increases by a factor, rho R, I should say, by 16-fold. So I showed this plot before. It's interesting to see what happens with regard to enrichment, because that's one of the things I can change. There are two curves here. One is for a mixture of U-233 and U-238. The other one is U-235 and U-238. On the x-axis, we have the enrichment fraction of uranium-238, which is the stuff that doesn't fission. And what you see is that as that goes up and up and up and up, the amount of mass that you need, let's say for the U-235, goes basically, in math terms, we'd say that diverges. Okay, it goes to infinity. Okay, so this is straight up what the critical mass is for U-235. If you're in pure U-235, it's only 47.5 kilograms, which is still rather a lot of material. Okay. And it's only 16 for U-233 because U-233 has a higher fission cross-section. Okay. So this is all for a bare metal sphere at natural density. This is before I push. Okay, this is what you need. So if you get this value, what it means is that that sphere is losing neutrons as fast as it's producing them. It's at that K factor of 1. That's critical. That's not a weapon. I need to make it go above that in order for it to start becoming a weapon. And by the way, even if I make it that first, if I put that critical assembly together, it does not, hold on 1 second, Mitchell. It doesn't immediately start. You need to put a neutron in. You need at least one neutron to start the thing. There's a critical assembly called Comet at the device assembly facility in Nevada. And when they first pull out all of their last control items and they have the thing ready to go, they literally wait for a cosmic ray to come along and create one neutron. And then it starts, okay? They literally have to wait. And sometimes they're waiting for a few minutes before it kicks in. Yes, Mitchell?
So what is U-233 role in making weapons?
What is U-233's role in making weapons? Good question. Right now, for us, basically non-existent. You could make a weapon out of it. It is fissile, okay, which means that as I lower neutron energies, its fission cross-section goes up. But you would need to make it. It's short-lived. It doesn't occur in any meaningful amount in natural uranium. But you could, if you could produce large quantities of it, it is a material that could be used. It has a high, because it's a shorter half-life, and it's a higher what we call specific activity. So it's also harder to work with. Okay, but it isn't quite as dangerous from a chemical perspective as plutonium. Okay. So this is a table. I don't like talking about tables for a long time. They're kind of, I put it out there. This just shows you the weight percentage of U-235. You see, by the way, as the weight percentage of U-235 goes down, the density obviously goes up. That means there's more U-238, so it becomes denser. This is the radius for a critical sphere of the material, the mass. This is the generation time and lifetimes. This is how long it takes for an event to happen on average that would increase your number of neutrons by the number of neutrons that are produced in fission. Remember what happens? Fission comes along, it creates a couple of neutrons, somewhere between 2 and 3, maybe 4. And then the time required for that to happen is the generation time. Reflection. Discussed this, I think it was with Bill. Okay? You can add a reflector that has the correct nuclear properties, and this too can increase your reaction rate. So, and we talked about this reflector material, should it have a large or small capture cross-section to capture neutrons? Small. Small. It doesn't want, you don't want to have it heat. How about the elastic scattering cross-section? Big or small?
Big.
Big. You should bounce it and come back. There you go. What kind of bigger building is small? I'll do stuff like that to you. Okay? No, but that's what it has to be. And it has to be pretty thick. This is not going to be a surface flashing that's going to do this because nuclei are small. You need thick layers of material to have any reaction rate. Mostly you just mix the nucleus. Okay? And reflection gives some of the neutrons multiple chances at inducing fission. This is a neat table that lists reflector thicknesses that's about 2 inches, right? 4 inches, 6 inches, right? That's rather a large thickness. And this is for different uranium enrichment quantities and for reactor-grade plutonium, fuel-grade plutonium, and weapons-grade plutonium. This is what the, for these different reflector thicknesses, you can see what happens to the critical mass. So, you know, it's clear that you get some boost here, right? If you go all the way up to a 15 centimeter thick layer of reflector, and this is almost certainly, I need to look at this, I think it's almost certainly beryllium, which is one of the best that you can have. You go from 11.5 kilograms required to create a critical assembly to only 3.71. But that's a lot. That's 6 inches of beryllium surrounding this thing. And remember, you've got to push the beryllium too. Now you made your job even harder. I'm not saying we don't do this, but it makes it's not as trivial as let's just throw a reflector in and we'll get there quicker. Yes.
So can you just explain like really simply what's happening? So we have your plutonium,
Yes.
uranium, and then around it you have your reflector.
Yes.
And then you're pushing it all.
And I push the whole thing and I compress it. And what happens at some point is I will get a neutron that initiates an event. I start creating more neutrons. And those neutrons can do one of several things. Remember the cycle of the reactor. They can get captured and just go away. They can scatter out and just go away. They can scatter elastically off of the plutonium. And that doesn't cause any fission, but they're not gone yet. Or they can do a fission. Okay? What the reflector does is that part that scatters out might scatter back in again. It might hit a beryllium on the way out and come back in again. It also, by the way, might not. It might hit the reflector and just go off at another angle, and you lose it. Does that answer?
Yeah.
Okay, think of it as a ball. I give birth to neutrons in the middle of this ball. They come out, they start moving their way out, bouncing off of things. This gives the reflector, gives you basically an opportunity for a neutron that managed to make it all the way out to here. It gives you a chance that it can be bounced back in again.
Right. Which is why the thicker means you need less in the middle because you're using it less.
Exactly. But if I put more thickness in the reflector and I'm wanting to compress all of this stuff, it's going to be harder because I got to compress the reflector as well as the material. Okay. And then the reflector becomes more efficient. Yes?
Do you need 100% symmetry in your compression? Or
Great question. Do you need 100%? No, you do not, but you do lose as you go asymmetric. And that's because what's the neat thing about a sphere? It has the minimum surface area per unit volume of any shape in our three-dimensional world.
is the issue that material can come out, or simply that you don't get spherical compression?
If the material squirts out, I guess that's a problem separately. But really what it means is that your chances of efficiently using a neutron to induce a fission go down as you deviate from spherical. And one of the ways that I'm thinking about going in the next lecture is I'm going to use an example of a place where symmetry matters even a lot more. Very similar to this myth, okay? Because all of the physics is the same. And we can talk about it freely and openly and go into that in a lot more detail. Symmetry is a little bit less important with fission than it is with thermonuclear reactions, and we'll get into that. But in general, if you make it less spherical, you offer the neutrons more ways out. There's more surface area for them to leave. Okay. All right. So how does a fission weapon work? You start with uranium or plutonium or some other potential nuclides, and you assemble them into basically a supercritical reactor using explosives. Okay? That's what we have to do. So the whole ball gets rolling, and how we do the initial metal pushing is with explosives surrounding this. Now, there's two distinct ways that you can imagine bringing this together. I've told you about the utility of compression, but you don't have to compress. You saw those tables. You can create critical assemblies without the compression. You just need more material. Okay? So option number one is to bring pieces together without compression. Option number two is to compress a shell to higher areal density. Okay? Then what you want to do is maintain the confinement for as long as possible to maximize the amount of fuel that is reacted. Because once the system begins to blow up, what happens to its rho? Its areal density, to its density? Decreases. So what happens to the rate? Decreases. Exactly. Overall, you lose an exact similarly. So if I go to that initial R, instead of saying R divided by 4, if I made it R times 4, then my reaction rate drops by a factor of 16, and that's it. It's never happened. So basically, you want to push everything together, hold it there for as long as possible, reflecting as many of the neutrons back as possible, and hopefully reacting as much of the fissile material as possible, and releasing that 200 MeV of Q value in each one. So time is very important. One of the main ways that we do this, the explosives, they just go off. They're done. They push everything together. And then, remember Newton's laws. If you've ever had physics, an object at motion tends to stay in motion, an object at rest tends to stay at rest. Well, that's called inertia. We keep the heavy metals inertia keeps it assembled. This is called inertial confinement. And that's a big principle behind weapons, is to assemble it, and for a little while, it just stays there. It needs a strong force acting for a long time, not a strong force like nuclear, but a powerful force to push it apart, okay? And the inertia keeps it together. This is inertial confinement. Now, introducing pulses of neutrons at the point of supercriticality is obtained. That's a good thing to do. Because remember, even if you have a supercritical assembly, you need to start with one neutron. There needs to be something to start the ball rolling, okay? And if you can put pulses of neutrons in at the right time, when everything is assembled densely, then you get more, literally, bang for your buck. Okay. So, I actually like these two pictures. They're from up on D courses, compliments of Carl. We have the original Los Alamos primer. These are the hand-drawn figures that were there. There's two ways to do it. The gun assembly, which has limited or no compression, and an implosion weapon. Let's talk briefly about gun assembly, but I'm not going to spend a long time on this, although it's historically significant. It's not really significant. It may, by the way, have some impact. Gun assembly weapons can be made quite well from U-235, and they're actually a real risk from a proliferation or a non-state actor. Would be a gun type assembly. Okay? Well, Little Boy was a gun type assembly. Not our first device, but our first weapon. Okay? Here's this nice picture, which Carl got actually from Wikipedia. Beautiful lineup. I decided to take a picture with Little Boy being loaded at Tinian Island. Okay? Really, there's lots of different things here. Let's just talk about the important ones. Down here, you see these orange, these are in cutaway cross area. These are basically like individual, like weightlifting discs. That's the uranium-235 down there, and that's uranium-235 up there. Bring that assembly down here, and you've got yourself a critical assembly. And the way you do that is with explosives. You shoot this thing down like a bullet coming out of the barrel of a gun, and you assemble the weapon at the bottom. You assemble a supercritical assembly. But even that is not enough. What do we need to get the ball rolling?
Neutrons.
Neutrons. And there is something here called Polonium Beryllium Initiator. I'm going to talk about that next. Okay? This is 64 kilograms of U-235, a 15 kiloton yield. Okay? Let's go on to the implosion weapon. And really, yes.
Wait, how can that diagram exist? Like, isn't that just like how to
Oh
build?
my God, you're right, it's not there.
Like, isn't that like how to build a nuclear bomb if you have?
There's a lot of detail that's missing. I think that a lot of these pictures, there's a lot of stuff. I will make a general comment. There's a lot of stuff on the web. Some of it folks are not happy about. Some of it folks are perfectly happy about. This doesn't make me nervous. Okay?
Makes me nervous.
Okay. Well, the fact that this is on the web does make me nervous. I mean, actually, the weapons, they make me very nervous. Yeah.
Is the speed of these 70 important for nuclear?
How interesting. That's a good question. What do you think?
Given the fact that they use explosives to do it, I would say yes.
I think that now you get down to the point why you don't need to worry so much. The details of how you do this assembly, it is really easy to do this and have absolutely nothing of consequence occur. I mean, well, the explosives probably go off, okay? It is not trivial to make something like this work, okay? And this is one of the easiest things that you could do. And 15 kilotons is, I'll say this, although it could absolutely ruin your day, it's a fairly modest yield. Okay. Yes.
What are the explosives that they usually, is there like typical explosives?
There's a very wide range of them. And a lot of the design efforts that have gone on in countries has been focused on the explosives.
Like what are we, like, is there a specific one that's been used? Like those little boys,
You know, honestly, I don't know. I'm sure we don't use that anymore. We've gotten much better explosives. One of the big things that we look for in an explosive is an unwillingness to accidentally go off. Okay? A lot of our nuclear weapons design is predicated on the idea that the weapon should only go off after an incredibly well-scripted set of events happens. If any of them goes wrong, okay, it should not happen. One of the things that I uploaded is a list on B courses, is a list of accidents that we had. And there's one thing that's common to all of these accidents. Okay? There was no nuclear yield. Actually, we've been very successful in doing that. Okay? The devices that we make are very resistant to that. And part of that picture involves explosives. But it's not all of it. We make them resistant to accidents. Okay, implosion weapons. Okay, this is the picture from Wikipedia of the Fat Man device that was exploded over Nagasaki. 22 kiloton yield, only 6.2 kilograms now. And this time it's Pu-239. And again, in the core of this thing is something called a Apollonian Beryllium Initiator. Okay? All of these devices need a pulse of neutrons to be created at the right point in time after assembly has occurred. You don't want it before, you want it after. Okay? Here are some simple numbers, and we'll talk about the initiators. For a 22 kiloton bomb, we need to get about that many fissions at 200 MeV per fission. Okay? Actually, it's really about 160 MeV per fission, because some of the energy that comes out of fission is not going to cause a bomb, a big explosion. It goes out other ways. So that corresponds to something like 80 generations. Okay, if you think about it as 2 neutrons per generation, 2 neutrons, 4, 8, 16. It's about 80 generations. That's also about 5 moles, or 1 kilogram of 239 plutonium that has to be involved. How long do we have? Well, the temperature in the nuclear weapon is about 40 million degrees, which means, and you can calculate this, that the average velocity is about 78 centimeters per second. And if the assembly expands even by 5 centimeters, the reaction will stop. Okay, that's just, you'll go subcritical, it won't go on any longer. Now remember, the neutrons are born at an energy of about 1 MeV in fission. So that's a velocity of about 1.4 billion centimeters per second. And the time that it travels, that means that, roughly speaking, you're talking about a shape, 10 nanoseconds between collision events with these 1 MeV neutrons. If you put all this information together, you'll find that only the last few, and remember, it's 80 generations, it's really only the last few that give you any meaningful yield. If I took 22 kilotons and divided it down by 128, it wouldn't have done very much harm at all. Okay? And 128 is not that much, right? 2, 4, 8, 16, 32, 64, 128, that's 7. Instead of 80 generations, if I had 73, it wouldn't work. Confinement. You need to keep that thing confined and let it keep going. You'd win a lot if you could make it to 82, right? You want to try and confine that thing and keep it together for as long as possible. So using a separate neutron source greatly improves the efficiency. And that means in turn that you don't really need to hold things together as long. So early implosion devices used initiators that introduced more neutrons at the right time in order to speed up the multiplication process. Now, typical ones had about 11 grams of polonium-210. Okay, this is something that you can make from neutron capture on bismuth in a reactor. So you can make this thing, it's got 139-day half-life, so you can cook it for a while in a reactor, do a chemical separation, and now you've got polonium-210. Polonium-210 recently got some interesting notoriety. Does anybody know recently? Yes.
It's used to poison Alexander the Great.
Yeah, yes. It can kill ex-Russian spies. Or anyone. Watch your sushi. We might go into that a little bit later, actually as an example. And the reason why is that it's an alpha emitter. This thing is unstable with respect to alpha decay. It emits an alpha, and polonium-210 becomes lead-206, which is stable. If that happens outside of your body, your skin stops the alpha. If it happens inside of your body, that's not so good. It renders up lots of energy. And because it happens over 139 days, it does it slowly over the course of time, it just makes you sick. If I put it all in one place in your body, like in a tumor, I can use it to kill the tumor. And some of the most promising medical radionuclides right now are alpha emitters, particularly one called actinium-225, which we're working on. Now, around this thing, we have a ball and shell of beryllium. Okay? Beryllium is a very light material. It's Z equals 4. It actually occurs basically in one isotope, 9. Okay? And all you have to do is shock this system and mix it up. If you do that, a reaction will occur. The alphas from the decay of the polonium will interact with the beryllium, and they fuse temporarily and form carbon-13, which then emits a neutron and becomes carbon-12. This is what that cross-section looks like as a function of the energy of the alpha particle, and I've drawn a line where roughly the alpha particle energy is. So the alpha is born at a bit over 5 MeV, and so it already has enough energy that it can get over the Coulomb barrier of the beryllium and merge and form carbon-13. I don't need to heat this system up. I just need to mix it up. We use alpha emitters mixed with beryllium as neutron sources in our labs. Americium, which is what's used in smoke detectors, is an alpha emitter. We mix it up with beryllium, you emit neutrons. Okay? The efficiency is incredibly low. It's less than 0.1%, actually less than 0.001%. Okay? Why? The vast majority of these things do not go off. You create the outlet, it doesn't induce this reaction. Why? So this thing is about yay big, okay? But remember, the alpha particle's range of matter is only about 10 microns. Remember I said if it hits my skin, it stops it? So if you've got a ball of this mixed stuff, for each Apollonian nucleus that emits an alpha particle, only the berylliums that are really close to it can possibly interact with it before it slows down and stops. Okay? So they're very inefficient, but they do indeed create a pulse of neutrons. Once you, it's kind of like the, you know, those light sticks that the kids use on, well, those sticks, right? You crack it, it's like that. You crack it, mix it neutrons. Okay. Don't put this on your kids on Halloween. Okay. But you know, that would be challenging. It's okay. But that's what happens, and they work quite well. In general, these things, they don't always have to be beryllium, but that's one of our favorites. You can actually use carbon-13. That works pretty well as well. And then you merge the alpha particle in and it makes oxygen-17 and then loses a neutron that way. But we call, when we mix beryllium up with plutonium, we call it a QB source. So this would be a POB source. Okay, but there's AMB as well. Lithium can be used as well. It's got a weakly bound neutron, just like the beryllium ion has. Okay, initiators only require mixing to work. Now, there's a much better way to create a lot of neutrons, and this is something called boosting. Okay, in boosting, you mix two isotopes, often of hydrogen. This is the most common mechanism. This T and this D, you can't find them necessarily on your chart of the nuclides or on your chart of elements. This is hydrogen 2, which is the deuterium, and hydrogen 3, which is the triton. The triton is unstable and has a lifetime, a half-life just beyond 12 years. Deuterium is stable. It's 0.04% of all natural occurring hydrogen. If you mix these two together, you get a big release of energy and a neutron. Okay? The two of them, the DT reaction, this shows what the cross-section looks like. At peak, this cross-section, let's go back. At peak, this cross-section is truly huge. Okay? But I have to mix the two of them together. And remember that in this picture, this alpha particle was born in 5 MeV. It has enough energy to get in and initiate a reaction. In a normal environment, at room temperature, the triton and the deuteron don't have enough energy to get close enough for that nuclear force to take over. They don't get to within 5 or 6 Fermi. And so it just doesn't work. I could have a container of deuterium-tritium gas right here and shake it as hard as possible, and this thing is not going to go off. It can't. Okay? It might burn, actually, if I open up its hydrogen still, but it won't do anything nuclear. I would need to get the atoms in there, the nuclei, moving much faster. Okay, and you can see that here on this cross-section curve. As the energy goes down, look at what's happening to this curve. I mean, we stop here at 10 to the minus 32 square-meters, but it just keeps going. I mean, literally, this thing goes down to effectively 0. Okay, so I have to warm it all the way up to get it there. How do I do that? How do you warm up gas? Well, there's many ways. Try to shoot a bunch of microwaves into it, but that's going to be really hard. One of the principal ways that you warm things up is to do what to them? If I have a bunch of gas in a container, what do? You want to compress it. That's right. Compress it enough, and you will get the temperature high enough that you will get to take advantage of that 5 bar in cross-section. Okay. So the whole goal is to get things going, compress it, and get boosted into the picture. But you need that high temperature in order to get it started. If I could just take deuterium and tritium and shake them, okay, they would fast enough. It would be pretty violent, okay. The thing could just start going off, but then immediately it would blow itself up. And what happens when a compressed gas is suddenly allowed to expand? What happens to it? It cools off. And so once again, it would just turn itself off. So you need to confine everything and keep it there for a long time so that it can sit and burn. Okay? Then it can burn actually quite efficiently. Okay? So let's put all these pieces together. The order of events has to be correct. You compress the uranium and plutonium using conventional explosives, right? You pull everything together. The initiator is mixed by the implosion, and during compression, actually, the DT gas is introduced in. You put all of this in, and this is what we would call a primary. Okay. So modern primaries have this boost as a feature. Okay. That boost, it does release some energy, but it's not the energy in the DT reaction that we're interested in. It's the neutrons. It's that extra neutron that's formed at high energy and is introduced right in the center of this compressed sphere that allows you to increase your efficiency for burn. And in all of this, timing is everything. If you get something out of order, it just doesn't work. Okay? So a lot of stuff is about everything happening at the right time.
So with either initiator that we use, do they put like enough of this in each weapon so that their lifetime is infinite, or is this basically like an expiration date?
Oh, that's a great question. Is this an expiration date? It absolutely is. Tritium, well, deuterium isn't stable. If you use an initiator, it's 139-day half-life. Your yields go down over the course of time. Tritium is a big one. 12.33 years, I think, is the half-life. You need to be replacing it all the time. It decays into helium-3, which is also valuable, and it's all right. But you need to be making tritium all the time and replacing it. It's often, that's a continuing elimination stockpile. Okay? Because if you want to try and make small and efficient weapons, you need boost. The only way to make it happen. Okay. So once we have the primary going, we can use the energy from it to compress and ignite. I don't like using that word. It's not a conflagration or burn. The secondary. Okay? This compresses. There's an explosion. This channel sends energy from that weapon over to the secondary. And then that gets compressed and it goes off. So the big difference between the secondary and the primary is that we don't need explosives to get this thing going. Well, I guess you do. The primary is the explosive. You need that first weapon to get things rolling, to get the compression going, so that you get that second part of it to go. And this is often called a two-stage device. Okay? There's two separate stages that go on. So a secondary really does work on the same principle as a primary, but it uses energy from the primary for compression. Some secondary designs, in addition to having, say, a thermonuclear interior, a DT interior, they also have some sort of a fissionable material, U-235 or U-238. And now it can be U-238 because the neutrons from DT fusion are high enough to make that go. They have an external shell of that. So not only does the secondary itself with DT in its middle burn and give you a release of energy, but it then creates another hit from this outside layer. In addition to that, in some designs, you can even have another layer of uranium outside of that. So in the end, a large fraction of the energy produced comes from fission reactions. Okay. However, a neat thing can happen with secondaries as well. You can make a design where there is no outer layer of uranium or plutonium. And if you don't have that, and you just compress and run the secondary alone, okay, with its DT fuel load, for example, if you just do that, then it doesn't have a lot of fission yield. And why is that advantageous? What does fission produce? Fission products. And their lifetimes are what? Well, some of them start off as milliseconds, but then they decay to things that are unstable, which have more like seconds, which decay to things that are unstable, which have more like minutes, which decay to things that are more stable, but still not stable. Some of that stuff that you have coming out would be something like strontium-90, right? There's a lot of talk about that during the Cold War. Strontium has chemical properties that aren't that dissimilar from calcium. And so if there's strontium-90 in the soil, and you can, in cows, the grass that grew in the soil, milk from the cows has strontium-90 in it, and we're poisoning babies. Anybody drinks milk. I mean, so really, fission makes a mess. Thermonuclear fusion does not. Okay. And we'll talk more about that later. And so in some sense, from a military perspective, especially if you're going to plan a war on your allies' terrain, like Europe, okay, you'd rather not have a lot of fission fragments scattered to the four winds. You'd like to use as much of the uranium or plutonium as possible, as efficiently as possible, but then you want most of your weapons yield to come from that DT reaction. The DT reaction produces energy, produces a neutron. Now that neutron does activate things around you, but, and this might be an interesting thing to look at some point, it's a homework problem. What really can a neutron make? If a neutron absorbs on your carbon, you're mostly carbon-12, it makes carbon-13, which is stable. If it absorbs on carbon-13, which is also plentiful in your body at some level, it makes carbon-14, and that's 6,000 years ago. Okay? I mean, almost everything in our environment, that neutron is not really activated in a very meaningful way. So if you go to a DT weapon, and it were a pure DT weapon, then it would just blow things up and not leave any significant fallout at all. It would just be a friendly death machine. Okay. And there is a lot of effort that went into these directions. There are weapons that were designed specifically to try to minimize the fallout field. Again, these are things that would have been used potentially in the European theater of war. I don't know if you'll discuss that. Let's not discuss that. But there were weapons that were designed to minimize that. Okay. But at least to date, we always need a primary to set the secondary off, and so there's some fission that's involved in that, no matter what. One other thing to mention is that there is a solid fuel alternative to DT. This is lithium-6 deuteride. So the neat thing about that, the DT has got this other problem. It's a gas. It's flammable, right? It is hydrogen, after all. So it's got issues of its own. Tritium decays. Lithium-6 and deuterium are stable. If you compress in the correct environmental conditions lithium-6 deuteride, the lithium-6 can react with a neutron, and you have a few of those around if you have a primary nearby. Okay? And it can undergo this reaction. It breaks, the neutron fuses on the lithium-6, makes lithium-7. Lithium-7 breaks up into an alpha particle and a triton. And that releases energy. That triton then goes and interacts with the deuteron, which was right nearby, and it creates even more energy from the DT reaction. So there are some real advantages to this. Lithium-6 is considered a special nuclear material. We keep track. Enriched lithium-6, we keep track of where it is, because it can be formed with lithium-6 deuteride. Okay. So a modern two-stage weapon, basically, this is my last slide, actually does a lot of dancing back and forth between fission and fusion. Okay? It starts with a conventional explosive, and then it goes down and compresses. The initiator basically undergoes a fusion reaction, like the alpha particles from the beryllium. And then there's fission from the primary that goes on. But remember, I've induced thermonuclear reactions by shooting DT gas in. That undergoes fusion. The neutrons from the DT go out and hit the shell. They do fission. Okay? Then we do energy transfer to the secondary. There's the secondary, and it gets compressed and ignites. And in many cases, since it has an outer layer that's also uranium or plutonium, it has both fusion and fission going on. Which leads you to the interesting point that it's fusion, fission, fusion, fission, fusion, fission. Okay? There's actually a lot of this ping-ponging going back and forth. Mitchell?
So the secondary is outside the primary,
It is outside, but it's within a casing and a channel that allows you to direct energy. It's inside of that casing. That casing isn't necessarily a reflector. That casing could just be another material. The casing could be uranium. You could maybe want to catch every last neutron that comes out and do as much fission as possible. It depends on what your goal is. If your goal is to make a lot of yield, you definitely need to put a lot of uranium or plutonium in. But a lot of nuclear weapons, this isn't their goal. You don't, the biggest weapon that was exploded was the Tsar Bomba, right? 200 megatons or something. It was ridiculous. It's not a useful weapon, okay? It's really not. Okay? Even our largest weapons, like Castle Bravo, are 50 megatons. It's not useful at that size. What you mostly want are smaller weapons that are compact and robust and safe. Safe. That's really like a really big deal. You don't ever want the weapon to go off by accident, okay? And the designs are actually to try to drive that yield number to somewhere comfortable, where you do damage to a target, and yet you can still get in there afterwards in a military way, because you do want to do that, okay? And that's another thing, just to be clear, we will talk about radiation effects later. I just want to be clear about this. Right after a nuke goes off, really in relatively short order, depending on the nuke design, you can have people in there. They will get dosed, there is no doubt, okay? But will they die? No. In fact, if you do it correctly and you do it quickly enough, they won't even get sick, okay? Remember at the end, this is something that sort of is missed in this technical discussion. These are primarily, hopefully they remain just strategic weapons, but they do have technical roles in certain settings. And you really don't want them to just be an Armageddon device. They're something that's used in designs of horrible warfare, but that's what happens. Okay? And when you're doing that, you want to design it for the right impact. So often yield is not, it's not just can I make the biggest yield weapon? Can I make a safe pinpoint design delivered correctly to where I need it to go that delivers just enough to do the job I want it to do, and then it's quiet afterwards. That's what a useful weapon of mass destruction would look like. Okay. Like kind of a morbid sort of note. That's the end of my technical discussion. We've got a few minutes here. I thought we would. I guess Michael didn't quite get around to finishing his lecture, so I was going to let him do that. But I want to allow it's been great. There's been lots of questions about this committee this morning, and that's been really good. So are there more questions here at this moment? Yes.
Is this a containment vessel there strong enough to contain the primary, or is that something that happens too fast to matter?
Is it strong enough to contain? Well, to contain the primary completely, that would be nice. Nice that it just did that. No, it contains it long enough. So most of this, remember that the neutrons that are born from fission are moving at about an MeV. They're moving at a decent chunk, like 3% of the speed of light. This device just needs to hold together long enough for those neutrons to rattle back and forth a few times. Well, more than a few times, but not a lot. Okay, the speed of light is awfully fast. Okay, so when you look at, there are calculations, very sophisticated things, 3D hydrodynamic instability calculations that I've seen of these devices going off. And it goes through great detail what goes on, and very realistic looking pictures. And we benchmark these things, not me personally, but I know people who've done this. And what you see is at the end, and the end is, primary is long since gone. Primary is a cinder, okay? The secondary compression has gone on. Things have gone on in there, and you've seen the results. And you just begin to notice that the case is no longer a beautiful initial shape. It's looking deformed. It's bulging at the center, kind of like Mount St. Helens looked like right before it exploded. Okay, so really the time scales for these processes compared to these hydrodynamic things that are going on, the nuclear stuff is all really fast. Okay, really a lot of the same physics that goes into this is in inertial confinement fusion. like a place like the National Fission Facility. And my plan going forward, rather than talking in great detail about the testing that we did here in America, is to talk about how we were doing testing at NIF. Because all of the same signatures are looked for. The DT reaction gives me a gamma ray sometime. I look for that. The neutrons, I want to know when they arrive because that tells me their energy. And we have all these diagnostics, and our big lead one, which is radiochemistry, which is what kind of radioactive debris do I get out? Does it tell me about the device? Okay. But in general, the time scale of the disassembly of the casing is much longer than the weapons time scale. Questions?
Lee, you just want to mention really quickly what you mean by special nuclear material.
No, thank you. And I haven't defined that before. This is special. This is materials that have potential use in nuclear weapons. Okay. Now I'm going to tell you something shocking here. Steel is used in nuclear weapons, but obviously we're not going to call steel a special nuclear material. Special nuclear material is subject to restraint and, more importantly, accountability. We try to keep track of where all of it is. Plutonium-239, uranium-235, uranium-233, lithium-6. These are all special nuclear materials. We keep track of them. If you have more than a certain amount in one location, you need certain controls. Those controls can vary from just being really careful about your inventory in a very ordered fashion, to needing to have guards with guns, to needing to have like this thing in a sealed up, safe environment. Large scale quantities of special nuclear materials really need to be in just one of a few places in the country in general. Okay. One of them is the device assembly facility on the test site, for example. That's where I've seen most of that material. But special nuclear materials are one of those things. Lithium-6, U-235, U-233, U-239. There's a few others as well. Okay, so I'm going to give Michael a little bit of time here. I think you were at this slide or one back. Right here?
Yeah.
Go right ahead, Michael. This is just what you saw before, except that it's on my slide format.
I wanted to mention one thing that came up in discussion. Several of you raised this question. So if you're looking for U-235, you obtain that through devices such as the gaseous centrifuge plant. You separate out, like the cream in the milk, you separate out tiny amounts of U-235 from the U-238. And that's the fissionable material that we use for weapons. For plutonium, which is not found in nature, if you operate a nuclear reactor, the fuel rods of the reactor contain tiny amounts of plutonium-239 and can chemically separate that out from the rest of the material in the fuel rods. So those are the two main ways to obtain weapons-grade material: the gaseous diffusion plant for uranium and the chemical reprocessing plant for plutonium. And the key area, we didn't quite get to this, we might talk about it later, was one of President Obama's major initiatives were called the Nuclear Security Summits, which were intended for countries to surrender their weapons-grade material to either the US, Russia, or to some general depository. And a lot of this was plutonium. And you want them to surrender it because otherwise that material can be stolen, could be used possibly by terrorist groups or by other countries. Now, going back to the issue of what this is about, the whole business about non-proliferation, we could discuss this, or recent nuclear weapons. I think we did discuss Israel, India, Pakistan, DPRK, and Iran very briefly. We'll get more into the DPRK and Iran later in the semester. Obviously, this is a very important and incendiary competition between India and Pakistan. They're two arch rivals. Pakistan was created out of India Pakistan is Islamic majority country. India is a Hindu majority country. And they have remained rivals ever since they were created in 1947 from the British Empire. And there have been several conventional wars that India and Pakistan have fought. India has won every war because of its conventional military superiority. So Pakistan is looking for nuclear weapons to counter India's superiority. So this is a geopolitical as well as a religious conflict. By the way, India has a huge Muslim population. India has a larger Muslim population than the population of Pakistan. But still, India has 1.3 billion people, so it has a majority of Hindus. So every one of these creates special technical and geopolitical circumstances. Israel versus its Arab adversaries, and Iran, which is not an Arab state, but also an adversary of Israel. Iran has official policy to destroy Israel. That's an official government policy. India, Pakistan, a separate rivalry. DPRK separately from the whole relationship with South Korea and Japan and the United States and Northeast Asia, and then Iran. And how do we move beyond this business? Okay, so let's see, we have 3 minutes. One of the big concerns about the spread of nuclear weapons beyond North Korea is, will that stimulate further nuclear proliferation? Candidate countries include Japan and South Korea, who might feel that the U.S. security guarantees are less credible to them if we allow North Korea to have their own weapons. Not that we can do much about it, it's not yet clear that we can do much about it. And in the Middle East, Saudi Arabia, the U.S., actually there's major stuff on the web just today that the U.S. is talking about providing a large number of nuclear reactors for peaceful purposes to Saudi Arabia. But again, the peaceful nuclear reactors, if they had the chemical reprocessing plants, could lead Saudi Arabia to have access to the weapons-grade material. And the other thing that's happened in the Middle East of late is this huge geopolitical rivalry between Saudi Arabia and Iran. A lot of the conflicts in the Middle East, I don't know if you're following this, in Yemen, in Syria, elsewhere, are rivalries between Sunni Saudi Arabia and Shia Iran, between Arab Saudi Arabia and Persian Iran. They're bitter adversaries. There's also Turkey, not an Arab state, but an Islamic state. It's a NATO ally, but also with great independent policies, different from the United States and elsewhere, and Egypt, a largely Sunni Arab state. So there's a hornet's nest of potential candidates for nuclear weapons proliferation in Northeast Asia and the Middle East. U.S. policy has been the greater the number of nuclear states, the greater the likelihood of nuclear weapon use. Except during the Trump campaign, he actually made a statement saying maybe it's better if Japan and South Korea had nuclear weapons. But he's back, he hasn't emphasized that since. I mean, Madison, the master, got to him afterward. He calmed down on that issue. There's a major literary debate on this issue. Ken Waltz, who's a professor of political science here at Berkeley for 30 years, wrote a very prominent piece called Nuclear Proliferation, More May Be Better, in which he argued that the stabilizing nature of the U.S.-Soviet mutual deterrence relationship could be replicated in India, Pakistan, Israel, Iran, and so forth. But this is hypothetical. And Scott Sagan at Stanford wrote a long piece critical of the Waltz position. So there's a bit of an academic debate on this. Not a huge debate because there are very few who support Waltz's position. No U.S. administration, from Truman through Trump, has supported nuclear proliferation. There are a bunch of countries who went down the nuclear road and gave up for various reasons, and they're interesting case studies. They include South Africa, Italy, Sweden, Brazil, Argentina, and probably some others. Each one is a separate story. There's a book by a man named Mitchell Reiss, R-E-I-S-S, who's quite a prominent figure in the literature, and he also was at senior positions in the George W. Bush administration. And he's written on why countries gave up their nuclear weapons appetites. Oops, I just screwed that up.
You just went back.
Thank you. Finally, there are other questions about motivations. I've asked you to read the Vipin Narang book, and he talks about 3 different categories of nuclear weapons proliferation motivation: analytic posture, assured retaliation posture, and asymmetric escalation posture. They're defined in the book. I won't discuss them now. I may come back to them later. Actually, I will. I'll have a session on nuclear proliferation of the middle powers. And finally, I want to mention something which is not in the readings, but is becoming quite a prominent discussion in Washington and elsewhere, is that Russia has established a doctrine whose validity remains open to debate in the United States, called escalate to de-escalate, which would be the use of a limited nuclear weapon after conventional attack, a conventional attack to deter NATO conventional counterattack. You may know that Russia has deployed large numbers of troops on the borders of the Baltic countries. One of them was the largest deployment since the Cold War. And what's worrisome is that some of the writings of Russian military experts talk about the notion that Russia, could attack Estonia, which is right contiguous to Russia, with conventional weapons, easily overcome Estonia, and then use a nuclear weapon, basically to tell NATO to keep out. So instead of having the idea of nuclear weapons are used for last resort and all that, this is nuclear weapons initial use to deter counterattack by NATO. I'm rushing to this is quite a significant development here, which is shaping the nuclear posture review and Trump's nuclear security strategy. So these are some of the additional ideas on nuclear weapons proliferation, which I wanted to get to before I ran out of time. Okay? Any questions or problems or issues? Do read Vipin Narang's account of the different motivations of nuclear weapons proliferation. That's required reading. Okay, thank you.